This is the notes for section 6.2, and we introduced this lesson yesterday. We talked about what the degree of a polynomial means in terms of how many possible times a graph could cross the x-axis. We threw some terminology at you, like what does it mean to be the zero of a function, and we're just going to review that, those thoughts using this graph. So on your graph paper that I've given you, I want you to put those 3 dots on the x-axis in the same place that I've put them. So you're going to make a dot at x equals positive 1, x equals negative 3, x equals negative 4. Okay, so somebody tell me what those 3 numbers represent. Yes, sir?
The zeros.
The zeros of a function. Very good. They also represent, yes?
The x-intercepts.
The x-intercepts. Very good. They also represent, yes?
Solutions.
Wow, you guys are really good. Okay, all 3 of those, the solutions to a function solving for x, the x-intercepts, the zeros of a function, all synonymous terms for the same thing. So what I want to do, because you're going to be doing something like this on your homework tonight, if we know what the zeros are, and we do, how can we come up with the function? Okay, so what I want you to think about is each one of these numbers will make a linear binomial equal 0 if they're substituted in for x. Okay, I'll get you started. For example, it's going to be a function, so it's going to be y equals. The number 1, when plugged in for x into a linear binomial, will cause that linear binomial to be 0. So that linear binomial must be x minus 1. If I put 1 in for x in this binomial, what do I get? I get 0. Remember, 1 is considered to be a 0 of the function. Okay, so Jake, give me another linear binomial that I could use.
X plus 3.
Very good. X plus 3, because if negative 3 is plugged in for x here, I get 0. And there's one more. Emily. X plus 4. Okay? Now, we're going to be reviewing a little bit of what we did in the previous section, because in some cases, this section will give you the zeros of a function, and you've got to come up with the function in standard form. So, any thoughts on how we can go from this factored form into the standard form? Remember what standard form means? Highest to lowest exponent order, no parentheses. So what are we going to do? Go back to your previous section homework. Remember a couple nights ago, you had to do some of this. Well, you probably thought of, well, let's group a couple of these together, and we're multiplying 2 binomials together, so that means we're going to use the FOIL method. Okay, go ahead and do that on your paper. Multiply those 2 together. It really doesn't matter how you group them. So Nick, do you have the result of FOIL on these 2 yet?
X squared plus 7x plus 12.
Nice. Okay, well, let's see. Chloe, can you tell me now what we would do to get it in standard form?
X squared plus 7x plus 12 by x minus 1.
All right, and that really means we're going to distribute both of these separately. We're going to distribute x all the way across to each one of these. So I'll go ahead and do that. Just write down what you would get distributing x to each one of these 3 terms. And then continue distributing with -1. So you should end up with 6 total terms after these are multiplied together. And from those 6 terms, you should be able to combine like terms. Erase this. And we're going to put our standard form down. I'll just put it over here. Hannah, what'd you get for standard form?
Y equals x cubed plus 6x squared plus 5x minus 12.
Okay, who got that? Awesome. Any questions? So again, that's a review of what we did a couple of nights ago. Okay, so I've got this function, which was the factored form, which came from the zeros that I was given. And then we know how to take that and get to standard form, just multiply. Okay, now, in some cases, you're going to be asked to graph these polynomial functions. Now, the book is going to say by using a graphing calculator, but you're not going to use a graphing calculator. You're going to graph these using the method that I'm about to show you. Okay, so when you start to graph these polynomial functions, you start immediately with the zeros on the x-axis, just like we have here. And then before we start having to calculate some inputs, put some inputs in, calculate the outputs, there's a pretty easy point that I can plot without having to do anything other than observe the function. I don't have to plug anything into the calculator. I can just see it. Give me that point, Reagan McCain. The y-intercept, which is -12. So whatever the constant is, if you're looking at standard form, you always know that that number on the y-axis is one of your points on the graph. And I know you only have 9 lines on the y-axis, so you can just draw 3 more at the bottom. Okay, now when you're doing these for your homework, I want you to start by trying to figure out what the graph is doing in this range between your x-intercepts. And then we're going to talk about what it does on the extreme left side and the extreme right side. So to begin with, let's see if we can identify the behavior of the graph in this range, in between. Okay? So to start with, I'm going to use as an input into, really you can do either one of these, the factored form or the standard form. I'm going to use as an input -3.5. The reason why I'm picking -3.5 is because I want to pick numbers that fall directly in the middle, in between two x-intercepts. So right in between -3 and -4 is -3.5. So what I want you to do, either with the factored form or the standard form, if you need to use your calculator, that's fine. Tell me what your output is for an input of -3.5. Yeah.
Couldn't you just do -1?
Well, we're going to do -1.
Okay.
Actually, we're going to do something besides -1. Okay, so if you get a number, an output for -3.5, raise your hand and tell me what you got. Okay, how many of you got 1.125? 1.125. All right, so for an input of -3.5, x is -3.5, we got a y of 1 and then just a little bit more. And that's just a rough sketch. So just show that it's a little bit above y equals 1. Okay? Now, I want to know what happens from my graph in between this x-intercept and my y-intercept. So this range where I don't really have anything, I don't know what the graph is doing. I want to know what happens in between this range of numbers from -3 to 0. So what do you think I'm going to choose for an input? What is directly in the middle of -3 and 0? -1.5. So now let's do the same thing with an input of -1.5. And once again, you can use either the factored form or the standard form. Maybe Jake, do you have that? Chloe, did you get that? -9.375. Okay, so we'll do -1.5, and then 2, 4, 6, 8, 9, and then just a little bit more. Okay, so you can kind of get an idea already what this graph is going to look like. How many times are we going to cross the x-axis? 3. It's cubic, so right there we know, because it's a cubic function, we can cross 3. We might cross less than 3. Will we ever cross more than 3 for a cubic function? Okay, so we know that this is the way we're going to cross. These 3 points represent our x-intercepts. So how do you think I'm going to proceed connecting my dots? Do you think I'm going to start from here, or will I come from here? Anybody have a thought? From the bottom? Okay. So I'm going to come up this way, go through that x-intercept. Now the reason why we had to pick this point, -3.5, is I know I've got to come up through this x-intercept, but without that point, I don't know how far to go, how high. I mean, I can't just do a random curve. I need to know how far to go until I stop and then come back through. And picking that number for x tells me, oh, okay, I go that far. And now I'm ready to come back down. So how far do I go? I go through this point, keep going. Now what? Go back up through this. Okay, now let's talk about what happens on the outsides, the extreme left and the extreme right. Let's talk about the left. Will I ever come back up? Will I ever come back to the x-axis? No. So I can conclude that I'm going to keep going forever down on the left. All right, let's talk about the right side. Am I ever going to come back down to the x-axis? No. So I can conclude that I'm going to go, oop, that's terrible. I'm going to keep going up forever on the right. I'm going to give you something that I want you to put in your notes that is called, this is how you determine the end behavior for any graph. Okay, this is something that you'll probably use, not just in this class, but down the road. Okay, how do we describe what happens to the graph to the extreme right of our right x-intercept, and then what happens to the left, the extreme left of the left x-intercept? Well, there's 2 things to remember. All right, here's number 1. Number 1 is the lead coefficient. Now I need to stop for just a minute and make sure you understand what I mean by lead coefficient. Lead means it's in front. And what's a coefficient?
Number in front of it.
Number in front of the variable. So what I'm talking about when I say lead coefficient is that number right there, which is positive 1. Okay? So step number 1, if you want to analyze end behavior, what is the graph doing? Check out the lead coefficient. If the lead coefficient is positive, which in our case it is, then on the right side the graph will go up forever. I'm just going to word it as goes up on the right. Now, I'm not going to write the converse of that, but it makes sense that if the lead coefficient is negative, what happens on the right side? It goes down, okay? So you get the picture? So I'm just going to use the positive, and you can understand if it's negative, then it's going to go down, okay? Number 2. Number 2 deals with the degree. If the degree is odd, which is our case here, what's the degree? 3, okay? If the degree is odd, then the left side will do just the opposite of the right side. And our graph here proves that. So again, I'm not doing the converse, but let's just think about, well, what if the degree is even? Then they'll do the same thing, okay? Whatever the right side did, if the degrees are even, the left side will match it. Odd, they're opposite. You can kind of think of odd, opposite. Even, they're identical. They're the same, okay? I don't want you to graph this, but I just want to drive the point home. Here's a quartic function that I went ahead and graphed for you. Why does it go up on the right? Okay, several of you said that. Very good. The lead coefficient's positive. Why does the left side match it? The degree is even. So you get the idea? So those are 2 real simple ways to analyze the end behavior. Now, in between, we're going to have to do some calculating. We're going to pick the number in between. For example, how did I get an output of negative 15? And why did I plug in negative 2? It's right in between negative 1 and negative 3. Now, theoretically, you could pick any number you want for x because x is an independent variable. But I'm just trying to make it standard. Everybody's doing the same thing. All your graphs are going to look alike. We're just going to pick the number right in the middle of 2 x-intercepts. Okay? And you can see the same thing over here. I picked positive 2, got the same result. All right, we're not going to graph this one. Just for sake of time, but I'd like for somebody to raise your hand and just tell me what the end behavior would be if we did graph it. What's it going to do on the right, to the right of our extreme right x-intercept, and what's it going to do on the left? Micah.
The right side is going to go down.
Why?
Because the lead coefficient is negative.
Okay, the right side, it's going to go down forever because the lead coefficient is negative, and then what's the other side, the left side? Okay, everybody,
Up.
why is it going to go up?
It's the opposite of what the other's doing because reading up.
Okay, odd degree. So on the other side, I know that's kind of a rough sketch, it's going to do the opposite of the right side. Everybody get it? Okay, very good. All right, so in some cases tonight, you're going to ask, they're going to give you the zeros, and then they're going to ask you to graph the function, and that's pretty much the process. Okay, so let's go to some more specific homework problems. We're not going to do both of these because really this is a review of what we just did in section 6.1. They're going to give you a polynomial in factored form. Your job is to convert it into standard form. And actually, we just did this. I'll come back to it. We just did this when we started off with factored form, and we used multiplication to get it into standard form. So I'm going to try to save a little bit of time and not do it again unless you feel like we need to. Maybe you can just describe, Nick, what would you do on number 1?
Well, you probably group 1 set off. I do the polynomial sets.
Okay, so he said to pair these up and use what method?
FOIL.
Okay, so maybe we'll get to a certain point. If you used FOIL, that's x squared plus 7x plus 12. Now, Nick, what would you do?
You have to distribute with both x and -1.
Very good. He said distribute with x and then -1. That would give you 6 total terms after you distributed both. And then what would you do? Combine like terms. And just make sure that the exponents are in highest to lowest order and you're in standard form. Okay. I know you don't have to do this, but I just want to make sure we understand what's going on in this section. If this were a function, okay, I just made it a function. What are the zeros of this function? Maybe Morgan can help me out with that. If this were a function on number 1, I know it's not asked for, but we're just going to do a little extra. What are the zeros of this function?
1, -3, and -4.
Awesome. Okay, got another question. Reagan Adams, what are the x-intercepts on number 1? Same thing. I tried to trick her. She wasn't tricked. That's another way of saying what are the zeros. Okay, so Chloe, what are the solutions on number 1? On this number 1. Yeah, I just asked the same question a different way. Okay, I'm just trying to drill in your head that those are all synonymous phrases. Okay, very good. Can't trick you. All right, we are going to do these because we need a little factoring practice. So basically, this is factoring. It says to write the polynomial in factored form. So it's a review. The thing that's a little different is we just left a chapter where we were factoring quadratics. Well, now we're factoring, these are both cubic. But the factoring principles are the same. What do we always look for first? I think GCF, greatest common factor, right? Okay, so Olivia, can you give me a GCF for number 1?
3x.
Awesome, 3x. Okay, Olivia, if you factored out 3x, what would be in the parentheses?
X squared minus 6x plus 8.
Very good. Can we factor any more?
Yeah.
How?
If you write 3x, and then the parentheses would be x minus 2.
Okay.
Or would it be minus 4? I think it's 4. And then x plus, or minus, okay, it'd be either 4 and 2.
Okay. Factors of positive 8 that add up to -6. She got it right. Very good. And let's just continue on with what we were doing before. I know it's not asked for, but let me see. Jake, can you give me, if this were a function, I know it's not, but if it were a function, what are the zeros of this function?
+2 and +4.
Very good so far. There should be 3 of them.
-3.
So how do we know what the zero for this would be? How did we get the zeros for these two? Looks like we just set them equal to 0 and solve. Well, let's do the same thing for 3x. If we set it equal to 0 and solve, what do we get? Yeah, so our third zero is the number 0. I know that's confusing. 0, the number, can be a zero of a function. Because if we plug 0 in for x here, it makes everything 0. Okay, so what are the x-intercepts? 0, 2, and 4. All right, number 2. Let's see. JT, can you help me out with number 2, factoring?
You could factor out x in each term.
Okay, and what would that give you?
You get x times the quantity, x squared minus 2x minus 50.
Very good. And JT, can you factor any more?
Well, 2 factors from negative 15 are negative 5 and 3, which add up to negative 2.
Very good.
So you get x equal, or x times the quantity, x minus 5 times the quantity, x plus 3.
Awesome. Now that's a polynomial expression. Now it's a function. I know you don't have to do this. James, what are the zeros of this function? 0, positive 5, negative 3. And those are also known as? Close. X-intercepts. Awesome. Okay, you guys are doing great. Just ignore this because this has changed. I'll show you what the assignment is at the end. We did one of these earlier when we were working with the graph, so I'm going to give you the zeros of a function, and we're going to build the function in standard form from these zeros. So what you're trying to think of here is linear binomials, and think of 3 of them, where if these numbers were substituted in for x, remember linear means you have to have x to the first in the binomial. When these numbers are substituted in for x, each of those quantities would equal 0. So Reagan McCamey, give me one of those binomials.
X minus 2.
Okay? And let's see, Dylan, can you give me another one?
X plus 3.
Awesome. And I know this other one really doesn't need to be a binomial, but I'm just using it as an example. Nick, what would it be?
X plus 0.
Okay, now let's talk about x plus 0. Do I need x plus 0? What is that really? What's x plus 0?
X.
X. Any number plus 0 is that number? Well, here's what I'm saying. Is it necessary to write x plus 0? What could I write instead? Yeah, so I wouldn't mark that wrong, but I think it's better when x is a 0 just to show it as the monomial x. Okay, everybody get it? Real fast on number 2, let's see. Morgan, can you give me the polynomial function? Awesome. Now what we did not do is change the standard form, but we've done that so much, I think you know what to do, right? We got the factored form, now you're going to have to do some multiplication like we did before, like you did back in section 6.1 to get it in standard form. Any questions? Anybody? Okay, we're almost done. In this set of problems, you're not going to, yeah, you are doing the evens here. You're asked to find the zeros. And then I'm going to talk about what does this mean, multiplicity of multiple zeros. First of all, let's find the zeros. The easiest way to find zeros, pretty much in your case right now, the only way to find zeros is to get this in factored form first. Okay? For example, look at number 2. It's already in factored form. So the zeros are pretty easy, aren't they? What are the zeros? 3? Negative 1/2? Wow, that's ugly. Yeah, if we're looking at factored form, the zeros are simple. It's when we're not looking at factored form that the zeros are not simple. So we got to get this in factored form. So Nick, what would you do?
You would use the greatest common factor of x.
So what's the GCF?
X squared.
Yeah, and x squared goes into all of those,
Oh,
and that's the greatest common factor. So when you factor out x squared, what's in the parentheses?
it would be x squared plus 6x plus 8.
Okay, and can you factor any more?
Yes.
What would that look like?
X squared times the quantity x plus 4 times quantity x plus 2.
Okay, so Nick, what are my zeros?
X equals 0, x equals -4, and x equals -2.
Interesting. Because we've been saying that the degree will tell us how many zeros we should come up with. Well, he only gave me 3. So what's the deal?
Because it's like x squared. There would be
X.
like 2 solutions, but it's 0, so
It's 0 both times,
it's
right?
-0.
So what he's just described to me is what multiplicity means, when a particular number is really used more than once. In this case, which number? 0. So what we're going to do to finish this off is to say that the 0, x equals 0, has a multiplicity of 2. Does that make sense? So now if I do, it's almost like this. My zeros are 0, 0, -4, -2. That accounts for all 4 of the zeros I'm supposed to find. What if, I know it doesn't and it completely changes the problem, but just play along with me. What if this were x to the 5th here? How would that change my answer? Yeah, now I've got x equals 0 with a multiplicity of 5. So that's what this means when it says state the multiplicity of multiple zeros. On number 2, do any of the zeros have multiplicity? No. Do any of the zeros have multiplicity now? Yeah, 3 has a multiplicity of 2. You get it? All right, let's try number 3. Real fast. I think we can get through this. Who wants to factor this out for us? GCF? Reagan?
GCF x cubed.
X cubed, and that would give you,
X to the, or x squared minus 6x plus 9.
okay, and can we go any further?
X, okay, x plus, or x minus 3 times x minus 3.
Okay, now let's find the zeros. What are they? 0 and 3. Do either of these have multiplicity? Both of them do. 0 has a multiplicity of 3. 3 has a multiplicity of 2. You get it. All right, there you have it. Perfect timing. Great job. Period 4.
Yeah.
Shout out.